there, algebras, and welcome to your Chapter 13 Lesson 2 notes, all about geometric sequences. So geometric sequences and what is the difference between these and arithmetic is what we're kind of going to get into today. But geometric sequences, still looking at a group of numbers that are distinguished by a specific amount, this time called the common ratio or the R value. And each thing inside the sequence is called the term. So in our case here, 11 is the first term, or A1, our initial value. 22 is the second term, A2. 44 is the third term, A subscript 3, and so on. Notice again, we have ... being an infinite sequence. The difference now, as you can see, is we are not just adding to get the same amount each time. So this is not a linear relationship. This time with the common ratio, what we're doing is we are taking the second term and dividing it by the first term, then the third term and dividing it by the second term, and the fourth term and dividing it by the third term to get our common ratio. So this time, our change is determined by an R value, and what are we dividing to become? So let me just show you how this has an R value of 2. And you can probably see that that could be the same as we multiply by 2, multiply by 2, multiply by 2. But again, it's called the common ratio and figured out by taking the second term divided by the first term. So let me just do this real quick. So 22 divided by 11 and 44 divided by 22 and 88 divided by 44 is all giving me that exact same amount. 2 is our common ratio. Okay, so same rules kind of are applying here, but now we're doing this by dividing. So in sequence 1 here, we've got 1.5, 3, 6, 12, ... Well, the ... tells me this is an infinite sequence. And what I'll do to find the R is take the second term divided by the first term. So 3 divided by 1.5. Okay, so we think it's 2. How about 6 divided by 3? Okay, we think it's 2 still. How about 12 divided by 6? And there we are. Our common ratio is 2. Okay, why don't you try 2 and 3 right now? And then we'll come back and take a peek at how those turn out for us. All right, algebra, so I would like to show you what was going on in both of these sequences. You can see my work for the second sequence where it is a finite sequence because there is no ... here. And what I did was I took 50, divided it by 20. I took 125, divided it by 50. I took 312.5, divided it by 125. And notice every single time I'm getting 2.5 as my common ratio. So that got confirmed. Now, what am I doing on number 3? Well, definitely infinite. I see the ... at the end. But now my numbers are decreasing. And so sometimes that causes some struggles for people as they're trying this out. Oops. So just what I want to show you here, if I take 27 and divide it by 81, I get this repeating decimal. If I want to show that in fraction form, I would press math, enter, enter, and I will get 1/3 on my paper so I can match that up. If your sequence is given to you in a fraction, then you want to represent your common ratio in a fraction form as well. So next, sorry about that, algebras, the perils of recording during the day. Okay, so finding our next term. So what's next? Well, let's use the common ratio to then apply to some of our infinite sequences and find maybe the 5th and 6th and 7th terms in these sequences. So here, both of these are infinite sequences, and that's why we can use our common ratio to actually find more values in the sequence. But let's use this to find our common ratio here. So let me use our graphing calculator. And let's type in, so we've got 2.6 divided by 1.3. Okay, so 2, we think 2 is our common ratio, but let's keep going. So 5.2 divided by 2.6. Okay, 2, so far so good. 10.4 divided by 5.2. Great, we get it confirmed. Our common ratio is 2. So actually, because you can see that it's just multiplying by 2, let's take that 10.4 and just multiply 2 each time here. So now fill in to get 20.8, multiply by 2, fill in to get 41.6, multiply by 2 one more time, and we get 83.2. Again, since my sequence was given in decimals, I continued my sequence in decimals. So you can see on number 2 here that we are decreasing. Let's see how you do finding our common ratio and then the subsequent 3 terms in the sequence. All right, so go right ahead and give that a shot. Pause it here and give it a shot. So we can see that our common ratio could be considered 1/3, or you could consider it 0.3 repeating. Because this particular sequence didn't give us direction as to should my answer be in decimals or should my answer be in fractions, I did represent both. That would be a personal choice which way to go for that particular one. After that, I then just took and divided each term by 3 because 1/3, same as dividing by 3, to continue on. Multiplying by 1/3, same as dividing by 3. So now let's get into, okay, clearly this is not a linear pattern like the common difference was, like arithmetic sequences were. So now let's look at what is the type of function that this is being modeled. So find R first from this table. So let's just kind of peek at how we're going. This, of course, is my term number. My X value is going to be my term number. My Y is going to be the value in the sequence. So if I'm trying to determine my common ratio, I take 0.5 divided by 0.25. So 0.5 divided by 0.25. 2. Now let's take 1 divided by 0.5. Okay, 2. Now let's take 2 divided by 1. We know that's 2. So our R is 2. A to the subscript 3 means I want the third term in the sequence. So this is A to the subscript 3 right here. It's equal to 1. So let's really look at this, having just left chapter 12 and analyzed our exponential functions. We can see that if our base is the same and our exponent is the change, that we've got an exponential growth function occurring here. So geometric sequences are represented by exponential functions. Now, if I were to go and graph this, I would just remind you that this would be discrete on our graph. We would not connect our points because there are no terms in between each of these terms. There are whole number terms only, so we cannot connect and pretend that there are fraction and decimal terms in between. Those do not exist. So this would be considered a discrete graph if we were to do it. So let's continue on and look at our geometric pattern in an actual formula. So, of course, we've got A to the subscript n. That's giving us n is the term number that I want, so the nth term. R is going to be, I don't know where this disappeared to. R is going to be our common ratio. Oh, they're below. That's why. So A stands for our initial value, and R stands for our common ratio. And n stands for the term number desired, the term number that I'm looking for. And notice that is in the exponent, confirming that this is modeled by an exponential function. So let's go ahead and do this on example number 1 right here. So we've got -8, -4, -2, -1. Okay, why is this sequence geometric? Well, because we are not changing at a constant rate, we're instead changing at a constant ratio of change. And let's just prove that by taking -4 divided by -8. We get 0.5 or 1/2. -2 divided by -4, we get 0.5 or 1/2. -1 divided by -2, we get 0.5 or 1/2. So the common ratio is what determines a geometric sequence. In our case, our A value is -1. Our common ratio was 0.5. And because I was not given direction as to does this sequence come in fractions or in decimals, you could also use 1/2 if you truly wanted. Excuse me. Now we want the 8th term, which tells me that my n value that I'm going to be plugging in is 8. So a to the subscript 8 is equal to -8 times 0.5 raised to the 8 minus 1 power. And I get to just plug that right into my graphing calculator to get my value, my 8th term in the sequence. So -8 times 1/2 raised to, or 0.5. We said either of those would be okay. Raised to the 8 minus 1 power, which you know is 7. And this is what I get. If you want to represent a to the subscript 8 as a decimal, please by all means. Or you may represent it as a fraction because the sequence really didn't determine for me which to represent. So you can press math, enter, enter, and get this turned into fraction form. So -1/16. Either of those being the correct answer. Okay, let me do one more and then you'll do one more. Let me do number 2 for you. Okay, let's see here. We've got our sequence. It's infinite, so I can keep going. What is the 9th term? There's my n value given to me right there. So let's figure out what the common ratio is. 6.6 divided by 2.2 gives me 3. Okay, so I'm thinking my common ratio is 3, but let's just confirm that. 19.8 divided by 6.6. Did I do that right? I did not. 19.8 divided by 6.6. Thank you. Is 3. My common ratio of 3. Missing a decimal makes a difference. And let's see here. Let's divide 59.4 by 19.8 to get our common difference of 3. Fantastic. What's our A value? That would be 2.2. So let's plug all this in. We've got A to the subscript 9 is equal to 2.2, my initial value, times my common ratio of 3. So notice my base on my exponent. And I'm raising it to the 9 minus 1 power, which of course we know is the 8th power, but I'll still plug it in exactly as I'm showing it here, just to show everyone this is the stuff in the exponent, right? And here we go. We did have decimals, so we'll keep this in decimal form. So A to the subscript 9, or the 9th term in our sequence, is 14,434.2. Okay, pause it right here and try number 3, please, where we're given an infinite sequence and we need to use our A value, find our common ratio, and again, find the 9th term, so an n value of 9. All right, I'll see you soon with the answer. So as you can see, this one was a little bit on the different side. When we were in chapter 12 and analyzing our exponential functions, we did not look at negative bases. And this was for good reason. That just wasn't what we were currently studying. However, if you do have a negative base, you'll notice in the sequence what the outputs were they bounced between being positive and being negative, okay? Which is what would happen in a base that is negative. Because our particular value in our sequence was odd that we were finding, and my subsequent odd numbers of my sequence were positive, our answer ends up being positive again. So you can see the work that I did on my graphing calculator to get my common ratio, knowing what my A value was 5, and then the fact that I'm looking for the 9th term, I was able to plug all that in. All right there, algebras. You let me know if you have any issues. Let's do the accompanying homework. So 13-2 homework is what you need to be responsible for now. And we will answer any questions that you have as long as you ask them. So good luck. Let me know what you need. And I will see you for some mixed review next. Bye, guys.